Greetings. If you're watching video streaming, we're starting a little bit late because of computer problems. We had a copy of PowerPoint from Microsoft, and it wouldn't let us open it without a confirmation number, and nobody knows what that is, so therefore we're going to have to go with hard copy until we straighten this out with Microsoft. I wanted to review a little bit what we did last time, kind of to bring it to bring us up to date. Last time, and you'll notice that the overheads are a little bit fuzzy. The reason is because it's a printout that we're looking at as opposed to the computer screen. Okay, last time we looked at the idea of fuzzy logic, and we looked at some of the different fuzzy set properties and definitions. We kind of got halfway through this. So let's go ahead and talk about that. We talked about last time the concept of, can we move down this way a little bit? On this one. There we go. There we go. Good. No, down. Whoa, big finger. Okay, big finger. Okay, good. Okay, we talked about alpha cuts and how we used alpha cuts to make fuzzy sets crisp. And then about how we could go from a regular fuzzy set to a crisp set by simply performing a threshold at a given value of alpha. And we also talked about alpha and beta cuts, how we can use that for trivalent logic. So that was a topic that we talked about last time. We also talked about, I looked everywhere for the word crisp. So they're Krispy Kreme donuts. How many have gone down and stood in line at Krispy Kreme donuts? When my wife and I went down there, it took us an hour in a car to get there. Boy, they're good though. How many have had the Krispy Kreme donuts? Everybody? Okay. It's best to go down, I guess, around 4:30 in the morning, because I guess the wait is only about a half hour long. Has anybody been down there recently? No? Okay. You know, if they're a day old, 8 seconds in the microwave is what it takes to get them fresh, just so you know. 8 seconds. No more, no less. We have it down. And it tastes very, very fresh. So we talked about convex sets last time and convex combinations. And we did talk about, I definitely need a pointer because my finger looks like a whale up there. And how we would take two convex sets and using a third convex set, we would perform a combination of two fuzzy sets using a third convex set. And we found out that the fuzzy combination lied between the maximum and the minimum. And indeed, this is also a characteristic, if you remember, for the generalized mean. The generalized mean also lies between the maximum and the minimum between the two fuzzy sets. And it does turn out that for any point that you can draw between the maximum and the minimum of the two fuzzy sets, you can come up with a third fuzzy set to perform the minimum. That is, if we had one fuzzy set, let's see if I can do this. Oh, well. If we had one fuzzy set, and we had another fuzzy set, and we had two curves. We had the maximum, and we had the minimum. And we said that any fuzzy combination of these two convex sets was always a third convex set, which lied in the intersection somewhere in this region. So any convex combination would be like this. And the converse is also true. Any line that you draw here between the maximum and the minimum also corresponds to a fuzzy convex combination. And how would you do that? You would do that by looking at the percentage and where this percentage cut between the minimum and the maximum, whatever that percentage was the value that you would put down here for this combination fuzzy convex set. Okay? Remember that with the fuzzy combinations, we had any point between here and here was the lambda times the point plus 1 minus lambda times the point, and lambda controlled where you were between the 2 points. That's exactly what we do here, is we choose the value of lambda that gets us this point between this point and this point. That gives us our corresponding value of lambda down here for the fuzzy set combination. So that's what we mean by in terms of existence. For every possible curve that you can draw between the minimum and the maximum, there exists a fuzzy set by which this can be obtained. Okay, next topic. We have talked about crisp convex sets already, and we have defined the crisp convex sets. And we began to talk, I believe, also about the fuzzy convex set definition. A fuzzy set, if you recall, this should be in your notes, a fuzzy set is convex if all of its alpha cuts are crisp convex sets. If all the alpha cuts were crisp convex sets. We used last time the set of lakes that were deep and wide, and we said that that would correspond to some sort of membership that would look like this. And if we perform an alpha cut on a contour map that looks like this, where this is high membership and this is low membership, if we perform an alpha cut, that simply means taking and tracing along a contour. That's all we're really doing. So if we took the alpha cut for this corresponding value of alpha, we would get the actual crisp set corresponding to all of the points within here. Now this is a convex set, kind of the way I drew it is a paraboloid, in the sense if you take any 2 points within that set and you connect a line segment, that's totally subsumed within this convex set. And maybe the way that I drew it, all of these are kind of families of paraboloids, that each of the alpha cuts are themselves convex sets, and therefore the entire set is a fuzzy convex set. In one dimension, we said last time that a fuzzy convex set would be something like this. This turns out to be a fuzzy convex set. And that if we take a slice here, that we do get a crisp convex set, which looks like this. And this is indeed a crisp convex set, because if you take any point here, then all of the points lying between here are also within the set. So this is a one-dimensional crisp convex set. This is a two-dimensional crisp convex set. And if all of the alpha cuts are indeed convex sets, then we have a fuzzy convex set. We also said last time that all crisp convex sets in one dimension had a lower limit and an upper limit for their fuzzy membership function, and that all fuzzy convex sets for one dimension always look like this, with W possibly being infinity, L maybe being minus infinity, but all of them look like this, because if it were bimodal, we said we could choose a point within each of the modes. We choose a point here and a point here, connect, and we would get certainly points outside of the set. So clearly if we have two modes, it isn't going to work. So this is the definition of the fuzzy convex set. Now Zada was able to take the definition in his original paper. By the way, I put Zada's original paper online, and in fact much of the lectures that you're seeing now come from his original paper. In fact, if one takes an introductory course in information theory, one goes through Shannon's original paper. If one gives an introductory course in fuzzy logic, one goes through Zada's original paper. It's frankly that well written. But this is on the web now. This is actually a reprint, which is one of a reprint book by Lotfi Zada, by Jim Bezdek, that he did around 1993, and is actually fuzzy sets won a citation index. Anybody ever go to the citation index? It's online for UW students, and you look at who has referenced your paper. Zada, I think for 1990, one of the years in the 90s, won the paper that was cited most in the literature. because there was a boom of experience and interest in fuzzy sets, and everybody who wrote about fuzzy sets went back and referenced Zada's original paper. So this is his original 1965 paper, and all of the concepts that we talked about are introduced here. It's remarkably readable, as all good papers are, but he has, for example, the concept of the complement defined, the idea of subsethood. Remember, if one membership is smaller than the other, it's a subset. That concept is defined here. The fuzzy union is defined. The fuzzy the maximum is defined. The fuzzy intersection is defined, etc. So all of the original ideas are talked about in Zada's paper, and it's fun to look back and appreciate Zada's insight into this problem in this area. Okay, let's see, where were we? Fuzzy concept, an alternate definition. I want to give you an alternate definition which was given by Zada for a fuzzy convex set. If you notice, by the way, if you go through these slides on your computer and you're in PowerPoint and you download the GIF files and put the PowerPoint and the GIF files in the same folder, if you are in the presentation mode and you click on 13, that page will appear. Okay? Another window will open and that page will appear. But it has to be in the presentation mode. You know what I mean? The full screen sort of way of doing it. So these are actually hyperlinks, and if you store them again all in the same file, it will go immediately to it. Okay, the alternate definition given by Zada is a very interesting one, and it turns out to be equivalent to the property that a fuzzy set is convex if all of its alpha sets are convex. This is actually an easier idea to establish mathematically than is establishing mathematically that all the alpha cuts are convex. And it says as follows. If we have an arbitrary convex set, we'll see if we can decipher this. If we have an arbitrary convex set, then upside down A means for every. For every value of x1 and x2, we can choose 2 points. Now this would be x1, this would be x2. So up here would be f of x1. This would be f of x2. And f of lambda x1 plus 1 minus lambda x2 means what? All of the points between here. So when Zada says we evaluate this function over this interval, it means this function over the interval corresponds to all of the values that the fuzzy function takes on. It's all of the values that the fuzzy function takes on. So he says that all of these values must be greater than or equal to the minimum of these two. The way that I have drawn it, this is the minimum. So for this particular choice of points, lambda 1 and lambda 2, are all of the other points in this interval, do they always exceed this minimum value? In this case, yes. All of them are above that minimum value, aren't they? And if this is true for all values of x1 and x2, then the fuzzy set is a fuzzy convex set, and it's an equivalent alternate definition to saying that all of the alpha cuts are convex sets, crisp convex sets. So this is the concept of the convex set. Notice that it doesn't require that the function itself be a convex set. The function itself does not have to be a convex function. It does, however, have to be unimodal. You will notice, for example, if we had a fuzzy set wherein the membership function looked like this, we can always find a lambda 1 and a lambda 2. I'm sorry, an x1 and an x2. Wherein, when we looked at this, that there would always be points on that curve which did not exceed the minimum. In fact, all of the points here do not exceed the minimum, right? Therefore, this is not a fuzzy convex set. And in fact, it's true of all multimodal sorts of functions. So this is not a fuzzy convex set. And this is a fuzzy convex set. Now, you know the definition of a convex function? Let's see, how do I want to put this? A convex fuzzy membership function. Need not be a convex function. We need to distinguish between these two. The converse is true. It turns out all convex functions, if properly normalized, correspond to fuzzy convex functions, but the converse isn't true. Now, a convex function, for our purposes, will be any function that you draw, and then if you choose any points on the function, that the entire line lies below the function itself. This would be a convex function. Okay? So it's kind of like all of the points below the line itself form a convex set. So any 2 points that you choose, even on the surface, all of the line segments connecting those points will totally be subsumed in the set. Notice, however, that we can draw a function which maybe looks like this. Now, this is not a convex function because we can take 2 points here and we can draw a line, and this line is above the actual function. So this is not a convex function. It's not a convex function because there is a line segment between 2 points that actually lie above the function. And it's not a convex function, but it is a fuzzy convex function. The easiest way, I think, for me to see that it's a fuzzy convex function is clearly all the alpha cuts of this will be little boxes, right? All of which are going to be convex. All the alpha cuts of this will be little boxes, little rectangles, right? And the lower you take the value of alpha, the larger the rectangle is going to be. So all the alpha cuts are indeed crisp convex functions. But the entire function itself is not convex. So there's a difference between the normal definition of a convex function and the definition of a fuzzy convex function. Let's look at some other properties of convex functions. Any questions on this? If you have a crisp convex set and another crisp convex set, and you perform the intersection of the two, you always come up with a intersection which is itself a convex set. Think about that. If you take any convex set, let's call this A, and you take another convex set, which you call B, and we perform the intersection operation on the two, which is this, then that intersection itself is also a convex set. Makes sense geometrically. So, if A is convex and B is convex, then A intersect B is convex. Does this make sense, at least from a geometrical point of view? And could you prove it if I ask you to? Maybe. Okay, well, the same thing happens to be interestingly true of two fuzzy convex sets. This is also true if A and B are fuzzy convex sets. Then A intersect B if we use the Zada intersection, which is the minimum of A and B, is indeed a convex set in itself. I have a proof in your notes that you can take a look at. Anybody like me to go through the proof? You guys are not real big proof people, are you? You want to get this down and use it. I hope that's your motivation in life. Okay. So there is a proof on page 16 of the gifts. But at least let's give this a little bit of head service here. If we have a fuzzy convex set, there's a fuzzy convex set in one dimension, and we have another fuzzy convex set. There's another fuzzy convex set. And we take the intersection of the two. The intersection, of course, is the minimum. Just from this little sketch, is that minimum also a fuzzy convex set? Yes. Because that blue curve has all of its alpha cuts equal to little squares, right? So indeed, it does make sense, at least from a geometrical point of view. So here are other generalizations of conventional Boolean logic to, if you will, fuzzy logic. The generalizations are frankly very fascinating, and it's kind of incredible that they actually generalize so very, very well. There's another theorem that says if we have a convex set, I guess we've actually shown this, that we have a single mode, that if we have two modes, that it cannot be a fuzzy convex set. We've shown that over here. Okay, so we've taken care of that already. Any questions thus far? In probability theory, many times one talks about joint probabilities. You talk about probability density functions of the price of gold and the price of silver, for example. And it forms a two-dimensional probability density function corresponding to some mountain range or something like that, right? And that corresponds to the fact that if you want to find out that the probability that the price of gold is something and the price of silver is something, or within a region, you integrate the density function around that region. So I hope you know what I'm talking about when I talk about joint and marginal probability density functions. Is that right? Now, doesn't it make sense that there should be something similar for fuzzy sets? We can talk about the fuzzy set of lakes that are deep and wide. Shouldn't we also have the concept of just the set of lakes that are deep? Not deep and wide, but deep. And just like in the probability sense, if we have the fuzzy set of lakes that are deep and wide, But we don't want wide, we just want deep. There should be some way where we can get rid of that wide variable and just look at the one-dimensional fuzzy membership from the two-dimensional fuzzy membership function in order to get just the information function about wide. Hi. Oh, you got them. Big ones. Hey, thank you. Do you want these? We have our official big things. Okay. They're really big. Okay, we've gone through properties. Now we're going through shadows and crisp shadows. How many people know who this is? Just Ben? Okay. Anybody else? This was the biggest thing in radio in the 30s and 40s and 50s. There were pulp magazines about this character, and it was recently made into a movie about 3 or 4 years ago starring Baldwin. Which one of the Baldwins? Alec Baldwin. No one knows. The Shadow. Yes. The weed of crime bears bitter fruit. That's is how the radio show used to start. So yeah, this is the Shadow, and there are. It was actually very popular on the radio. It's how Orson Welles. Any of you ever heard of Orson Welles? Orson Welles got his start in radio playing the Shadow in the early 30s, and went on to Mercury Theater after that, where he did War of the Worlds and scared everybody on that Halloween. Okay. Anyway, this is shadows. So we're talking about shadows. We're talking about joint and marginal fuzzy membership functions. And it turns out that you get these marginals from the joints in a kind of a similar manner that you do with respect to a probability density function. If you haven't noticed it yet, something which will recur again and again in fuzzy logic is the use, instead of the multiplication, by the min operation. And instead of the addition operation, you'll use the maximum operation. In fact, we have seen that this is the Zada logic, and this is kind of the sum product logic. Okay? If we were to have a joint density function, probability density function, if we were to have a joint probability density function, say f of x and y, dx, dy. Whoops, no dx, dy. And we just wanted to get, this is silver, this is gold, we just wanted to get the price of gold out. What would we do to this joint to get the marginal? Anybody remember? We integrate out the variable we don't want. We integrate out the y variable. How many remember that from the joint to the marginal? Okay. Now let's just apply this because we're going to see this so much. It's it's fascinating. We're going to have matrix vector multiplications. You know how you do when you do matrix vector multiplications? You do this times this plus this times this plus this times this. Okay. We'll find fuzzy logic operations where you'll take the min of this, min of that, min of this, min of that, min of this, and then take all of those mins and do the maximum of them. So exactly multiplication replaced by minimum and addition replaced by maximum. So it's something which occurs again and again and again. We do a similar sort of relationship in terms of fuzzy membership functions. This, by the way, is called a projection because this is very similar to what you would get when you do a tomographic projection. When they're doing CAT scans, for example, you get one-dimensional information from two-dimensional objects by looking at how much the X-ray is absorbed as it goes through the body. You do a line integral of sorts. So this is a projection. Another type of projection is if we had a fuzzy membership function of two variables, say lakes that were deep and wide. Okay, this is deep and wide. This is the membership function of a lake of a certain width and a certain depth in the set of lakes that were deep and wide. So X is deep, Y is wide. And what we want is we just want a partial information out of it. We just want the deep part. Now, if we follow here, if we follow here, and we replace the multiplication by minimum and the plus by maximum, what we actually get here is, instead of the integral is kind of like what? A summation, right? It's a continuum sum. And indeed, what we get here is a maximum operation. A maximum operation over all values of y. So this is what I'm going to refer to as kind of the shadow. And this is more of a projection. But you will notice the similarity in flavor of this concept between the idea of probability density functions and membership functions. This was originally proposed by Zada in his 1965 paper. So this being the case, let's look at some ramifications of this sort of thing. Let's look at a couple of crisp sets. And we can look at the set of crisps, I don't know, the set of lakes that are between 6 miles and 8 miles wide. And I don't know, what's deep? 1 mile to 2 miles. That's pretty deep, isn't it? So if we looked at those set of sets, we would get a nice crisp set, a patch here, wherein if a lake was in this area, that this would be a lake between 6 miles and 8 miles wide and 1 mile and 2 miles deep. This would be a nice crisp set. Notice that if we just wanted the, if you will, the marginal membership function, this is crisp, that anytime we have a crisp two-dimensional set, then when we take the marginal, that marginal is always going to be either be 1 or 0, isn't it? Because if the line which passes down passes through the original crisp set, the line passing down passes through the crisp set, we can even get original and chop this off for some reasons we won't even say. But as we come down, if we hit a 1, we're looking at this path down here for 6 miles, and we're doing the maximum. Well, here's 0, 0, 0, 0, 0, 0, 1. Oh, 1, 1, 1. Okay, 1 is the maximum there, right? And as long as that line, which is dropping down, passes through a 1, then we're going to get a 1 down here. Because this is the mu of x and y, for this crisp set. And what do we say? This is deep. And w is wide. And we just want the deep, the membership function for the deep, for this particular crisp set. And the membership function, we said, mu of x is equal to the maximum of mu xy of x and y over all values of y. Which means that we choose a, let's see, do I have that right? Yeah. So that if we choose a value of x, for example, we choose this value of x here. We want the value for this. Then we have to look at this membership function over all values of y. Well, what does this membership function correspond to? Well, it corresponds to the membership function over this entire range of values for y, for this specific value of x. So we march along here and we find the maximum result, and that maximum result gets translated here. So you notice that the shadow concept for the crisp translates very nice. We notice that if we have a two-dimensional crisp membership function, that's going to translate to a two-dimensional marginal, which indeed it needs to. If you have a crisp joint, you would expect a crisp marginal sort of set. But the same thing exactly happens for convex sets. This is what we decided was the contours for deep and wide sort of lakes, right? So here we had a 0.1, 0.3, 0.6, 0.8, 0.9, something like this. So this is the contours for the joint membership function for lakes that are deep and wide. Now, we don't want deep and wide. We just want deep. So we just want the fuzzy membership function for mu sub x of x. We do exactly the same thing, except that now, along our contour, we take on continuous values. And we go up here, and I don't know, it looks like it keeps on going up, but maybe that's a 0.4 there. And maybe here is a 0.1. And here, the biggest number it gets is a 0.8. And over here, well, let's say that actually goes up to a 0.99. So if we did the marginal, if we took the maximum of all of those lines going down, in order to get the marginal membership function, we would get something which is like this, which is the membership function for deep. That's a good membership function for deep, isn't it? If we started out and I said, give me a membership function for deep lakes as a function of depth, you would come up with a strictly increasing function which looked like this. That's exactly what you would do. So we can see that this concept is very nice and intuitive in terms of coming out with marginal membership functions which are very akin to the corresponding joint density function. Of course, this concept extends to higher dimensions. We have, for example, if we could zoom in on this, we can have, for example, a three-dimensional membership function which projects down into 2, and this then would be its corresponding shadow. Or we could have a fuzzy membership function. This would be something like a Gaussian cloud. So this is a fuzzy membership function which is very high in the middle, and then it goes out very gradually. So this might be the fuzzy membership of points close to this point, the point right in the middle. It's the fuzzy membership function of points close to this point, right in the middle. And if we wanted to look at the two-dimensional equivalent to that, we would run down vertical lines. We would take the maximum along each of those projections and generate the corresponding two-dimensional membership function down here. So just like with joint, we can go from 50 dimensions to 3 dimensions, or 50 dimensions to 1 dimension, or 87 dimensions to 86 dimensions. We can do the same thing. So this, again, is the concept of the shadow and obtaining marginal fuzzy membership functions from joint membership functions. Okay, the next thing I want to talk about is fuzzy relations. I want to talk first of all about the definition of fuzzy relation. A fuzzy relation in X is a fuzzy set on the product space, the Cartesian product X cross X. Let's see if I can do this one. Got an overthrow. So we take a domain and we do a Cartesian coordinate, and we look at a relationship between the Cartesian coordinate and elements of the different Cartesian coordinate. Let me give you an example that I had. Let's see if I have it. Oh no. Okay, here's a set. Can we zoom in on this? Would you zoom in on this, please? Okay, good. Okay, we have 4 people here. Okay. We have Barbra Streisand, The Beast. Anybody old enough to remember The Beast? It's a TV series, Beauty and the Beast. Clint Eastwood and a primate. These would be our elements, for example, in our fuzzy set, our fuzzy relationship set. And what we have to do is, on a scale of 1 to 10, look at the interrelationships between them. So just as a fun sort of example, we have Barbara, we have the beast, we have Clint, and the monkey. Okay? So this is our x, right? So x cross x is the Cartesian coordinate which goes down here. So we have Barbara, we have the beast, we have Clint, and we have the monkey. By the way, I got these from a book. It was called Separated at Birth. And what they did is they had pictures of famous people and strange people that, or strange animals that look like them. So, okay. Now, relationship. What is the resemblance? We can talk about resemblance in terms of the relationship between these. Now, this is not a numerical thing. This is not something we might be able to come up with an ordinal metric of doing it, but just with eyeballs. First of all, I think you can see that the diagonal here is always going to be 1, isn't it? Right? The diagonal here is always going to be 1 between these. What about Barbara and the Beast? Let's take a look. What would you say? Point? Okay, 0.9? 0.8? 0.9? Okay. Now, do you think that this is commutative? Yeah, probably. It's commutative. That means that this table, this relationship table, is going to be symmetric about the diagonal. Barbara to Clint. What do you think? Really? I would put 0.3. Okay, what do you want to put? I don't want to bias, 4. Okay, we have 4. And then Barbara to the monkey. 0.6? What do you think? Yeah, about 0.6. Okay, let's have the overhead back here again. Okay, now Clint Eastwood to the primate. That's amazing, isn't it? 0.8. Clint. Oh no, that's the beast to Clint. The beast to Clint, I don't know, 0.3, 0.8. And then finally Clint to the monkey is 0.8. Oh, this should be 0.3. Wait. 0.3, 0.4, 0.8, 0.8, 0.6, 0.4. Okay. So anyway, here's our heuristic relationship matrix, which actually gives relationship among some different articles. What's interesting about the relationship matrices is the following. Many times you have a partial relationship matrix, and you might have the relationship, for example, between Barbara the Beast and Clint Eastwood. Okay, and you maybe have a racial relationship monkey, or relationship matrix. Relationship monkey. Okay. And then all of a sudden the monkey comes in and you only have the monkey's relationship to Clint. The question is, if you have one set, which is the relationship of Clint, Barbara, and the Beast, and then somebody comes along and says, now I have a relationship between Clint and the primate, can we use that information to extrapolate or estimate the relationship of the primate to Barbara and the Beast? Do you get the idea? And the answer is yes, we can do that. And that's where we want to go here. And I'm actually going to do it with a little bit something. I should have worked it out with those guys, but I didn't. I worked it out with these guys. Can we zoom in on here? Can we zoom in? Okay. Okay, these are just some cartoons I drew. These were Jim, Tom, Jim, and Dick. And here's the relationship between Tom, Dick, and John and Jim. Now you notice there's no relationship between Tom and Dick here. There's no relationship between Tom and Dick. There's just a relationship between Tom and John, and Tom and Jim, and Dick and John, and Dick and Jim. but there's no interrelationship between Tom and Dick. But, if we know the relationship between Tom with John and Jim and Dick between John and Jim, shouldn't we be able to determine the relationship between Dick and Tom? You get the idea? Let's see what we can do with that. Okay, we have John, Tom, no, I guess John and Jim. I have to actually redo this up here. Man, that's another one that's going dead. I wonder. Okay, I can do it. Thank you. There was a gasp from the crowd, except I don't have any markers now. Is there one here? Okay, thank you. Did I throw this one away before? That one fell off. Okay, good. Okay. John and Jim and Tom and Dick. So here we have a 0.8, 0.6, 0.2, and a 0.9. These are the relationships that I gave them. Now, here's the idea. Tom resembles Dick if Tom resembles John or there's a bunch of different ways we can do this. Or Tom resembles Jim. Maybe we should make this harder. And, because that's a harder statement, right? I'm sorry, or. And Dick resembles John, or Dick resembles Jim. I want you to look at that linguistic statement and see if you agree with it conceptually. So we're saying that Tom resembles Dick if Tom resembles John or Tom resembles Jim. I don't like that. Let me do it this way. Tom resembles John and Dick resembles Tom. Let's see. And Dick resembles John. Yeah, I like this better. You like this better? Or Dick, Tom resembles John, and Dick resembles John, or Tom resembles Jim, or Dick resembles Jim. Wait, what did I do? Dick resembles John. Dick resembles. And Dick resembles Jim, and Dick resembles Jim. Okay. Now, does that make sense? Logically, right? But notice that our logic is totally fuzzy because we're using fuzzy linguistic variable of resembles, right? So resemble is on a scale of 1 to 10. So let's look at the truth of this statement, Tom resembles Dick. If this is actually a logic statement, Tom resembles John. What is the resemblance of Tom to John on a scale of 1 to 10? 0.8. What is the resemblance of Dick to John? 0.2. And what do we have here connecting them? A fuzzy and, right? Min. So that's the first statement, is equal to the minimum. Now let's look at the second one. Tom resembles Jim. What do we have? 0.6 and 0.9. This is also connected by a fuzzy and, right? And then both of these statements are connected with a or, which is a fuzzy logic or. So here we have a maximum operation upon of these. So the degree to which Tom resembles Dick, we have interpreted from these fuzzy membership functions and our fuzzy logic, using Zada logic, is given by this result, which is 0.2, 0.6, looks like 0.6, right? Is the resemblance between the two. So therefore, by taking advantage to inner resemblances, we can do very, very interesting things. Any questions on this? Isn't that interesting? The ability to do that, and this is what we'll see again and again, especially when we get into fuzzy inference, is the ability to take logic, for example, if-then statements, and make them into math expressions. So we can reduce the linguistic statement to an actually numerical algorithm. Let's take another example. Suppose that I have two guys here, Tom and Dick. This is an example. This is in one of your GIF files, and John and Jim. And here's the resemblance matrix. I'm not even going to draw the pictures, but... Oh, that's the same one over here. Suppose there's two other guys, Harry and Frank. Okay? And I'm going to use the same Tom and Dick here. And I won't attempt to draw Harry and Frank, but just for purposes of illustration, suppose that these are given by as follows. You notice this Tom and Dick, again, is the same as this Tom and Dick. Now, these are relational matrices, and what we would like to do with these relational matrices is we would like to combine them and come up with a relational matrix of John and Jim and Harry and Frank. Now, John and Jim are linked to Tom and Dick are linked to Harry and Frank, so we should be able to combine these resemblances into a composite statement about the resemblance of John and Jim to Harry and Frank. You get the idea? And what it boils down to, believe it or not, is actually a min-max matrix multiplication, which I will show you. Envision with me multiplying these two matrices. And notice they line up, just like a matrix needs to, right? This row adds up with this column. So we're adding like things here. If we replace the multiplication by minimum and the addition by maximum, we have the minimum here, which is 0.8, and the minimum here, which is 0.1, and then we want to take the maximum of those two, which is a 0.8. Do you agree with that? So we perform regular matrix multiplication, except min replaces multiplication and maximum replaces addition. Here's what we're saying. John resembles Harry if John resembles Tom and Tom resembles Harry, or John resembles Dick and Dick resembles Harry. So we are actually, by this multiplication, interpreting a linguistic statement using fuzzy logic, using Zada logic. Can we go through it again? John resembles Harry if John resembles Tom and Tom resembles Harry, or John resembles Dick and and Tom resembles shoot. John resembles Dick and Dick resembles Dick. No, Dick resembles Harry. Okay, so we get the maximum there. So you get the idea. It's exactly the max of those two men's, exactly like we did before. And the logic it totally flows from our interpretation of fuzzy linguistic variables and Zada logic, if you will. And we can do the other ones. What about the relationship to John and Frank? Well, that turns out to be, minimum here is 0.4, 0.2, and the maximum of that's 0.4. We do this. That's 0.6 is a minimum, 0.1 is a minimum, so we get a 0.6 here. Similarly, we get a 0.4 here and a 0.6, which is a 0.6. So by performing this operation, we are actually finding out the relationship between John, Jim, and Frank and Harry using the fuzzy logic. What we have done here is a composition operator. In fact, I think you can see that we did a 2 by 2, but there's really no reason that you do a 2 by 2. Indeed, there's no reason even that the matrix needs to be square, as long as the matrices line up in a conventional way where you multiply them, right? Like if you had one relationship matrix that was a little bit longer than it was wide, your other one would have to be such that they match so you could multiply them together. And we could do it that way. So this is referred to as a compositional operation. If this is the matrix A, and this is the matrix B, and this is the matrix C, we write the matrix C as the matrix A with a multiplication that's a hollow dot, which refers to the composition operator. The composition operator. The composition operator is the combination of matrices using max for addition and min for multiplication. Use exactly the same operations, and we've seen it has a fuzzy linguistic foundation. It's exactly a interpretation. Now, some of the composition arguments, this is kind of interesting, is not commutative for the same reason that matrix multiplication is not commutative. In fact, when you commute them, notice if we commuted them here, that our Toms and Dicks wouldn't line up with the Tom and Dick over here, right? So it's a question of whether it even makes sense when you perform the commutation. Your dimensions have to line up here and here in order to perform the multiplication. If you flipped it around, they wouldn't match up. So it is not commutative. It is, however, associated. That the composition of A with B with C, well, let's use D since we've used that, is the same as the composition of B with D first. It is associative. But it's not commutative. Okay, any questions on this? So this is the first time we'll also see this happening in fuzzy inference engines, is the mapping of the linguistics directly to something numerical which we can evaluate. And we'll take a look at that next time. And you're dismissed. Any questions first? There's new homework on the web. You have some today that you can hand in, and there will be some due next week also. Thank you for your attention.